Sweden and of KTH and so. So Carlos actually has been doing many things over his career. He worked in the famous lab in Grenoble on adaptive control long time ago. We have a textbook in that. He worked on non-linear control, on automotive control. I first met Carlos in Lund when he was working on friction control. He came up with a new friction model, and then we shared some interest in network control. More recently, he's been interested in traffic and automotive. He even developed a very ambitious test bed in Grenoble with sensors along the highways and so on. But the last few years, he's been working on electric vehicle charging and building systems for that. So we are very much looking forward to what you're doing in this area, Carlos. So very welcome.
Thanks very much, Harry. My pleasure. Thanks so much for the introduction. I've been a friend of this colleague for a while. In '85, I spent 1 year in the Carostrom lab, and since then I have a lot of contact and used to come to Sweden. So today is about a vision, I would say, about what I think we need to deal with these arrivals. Now I don't use anymore the word of massive arrivals because I've been changed a bit, of electrical vehicles, and try to see how you can take the opportunity of exploring basically the batteries of these vehicles, but also the need to have specific models devoted to this, and in particular try to develop models which are scalable and practical. So my talk here is basically divided in 3 parts. So the first part is a little bit a tour about the problematics, I would say, or my vision that I have about that. The second part, which is here written the first part, is about more modeling. So this part about modeling is a bit more refined. We bring it to the scale. We have been developing 2 versions of a digital twin. One of them, the last one, is applicable for all France, and I will try to show you a bit some videos of how these things work. The second part is a bit more in the middle long-term vision, is the use of the so-called flexibility in the electricity markets. And I will formulate a couple of optimization problems that can be attached to the model and connected to the electricity market. I'll give you some. The second part will be more, say, academic-like it, but I think it's kind of paving the way for the next. Okay, so this is, let's start with, you probably know about these dot curves. It basically reflects the difference between supply and demand. So what you can see here in the left is the curves in previous years. This is the upper part, which is a little bit more flat. And with the arrival of renewables, there's more production during the early time to the sun. And then this curve goes down. And then when people go back home, there is need to recharge many things, among others the cars, but not only, you launch it, whatever the machine and so forth. And the production of renewable decrease. So it makes a variation, which is very important. So what is important here is not that much the values, but the fact that the curve is not flat. And that poses a certain number of problems, right? So the problems that impact the operation of the grid, the electrical grid, is that if the matching between the supply and demand is badly done, because there is a lot of uncertainties in the use of the energy, production of the energy, and that can cope with the change of the frequency of the operation of the network, and the worst destabilization of the network operation, right? So these things are not new at all, but we have been in Europe, in the States, different type of mechanism, there are mechanisms to compensate for that. And then you end up with the so-called electricity market that operates at different time scales. Basically, you have 3 time scales. I'll probably show here. So the first time scale, you have to react fast, okay? And this fast reaction is the order of magnitude, a few minutes at most, seconds some time, and it's called the primary reserve. And this is the one that we have been trying to study here. Then there is a secondary reserve, which have a bit more slow time reaction, and then finally there's a reserve. So there are conceptually, mechanically, different mechanisms to do that. The one that is probably most known is you have some generators that will operate fast as requested by producing electricity from gas or from other type of materials. Now, what is the role here about the electrical vehicles? I don't know exactly where I can put myself, but so the notion of flexibility, what else, is that because this variation of demand and supply requires to make the system optimal or to optimize the system requires to store the energy. When you have too much, you eventually take out energy when you need. And the concepts, so vehicles, electric vehicles, as we mentioned here, could be seen also as an option to storage exceed of supply of the energy. Now, there is many technologies on how the vehicles may potentially interact with the grid. And here, there is a list of different levels of automation in terms of connectivity between vehicles and grids, okay? So this is what is done today. So basically a full price, you go, you plug, and you get recharged. And then the other stream is the potential to have dynamic pricing. And of course, using the connectivity, bidirectional connectivity between vehicle and grid. So it means that you can flow energy in one direction and recover energy in the other if needed. In my presentation, the second part, I'm not using really V2 grid because I am not using the batteries to feed energy back. I will talk about the kind of reserves, which means that you can modulate it, the injection of energy. It's not necessarily injected constantly, but you can sometimes inject a bit more that you request or inject a bit less in order to play with this difference between supply and demand. Now, this is a bit of picture I like to show often because they say, okay, well, you think in your own vehicle, right? So how much my own vehicle can produce energy, very little. But now if you put in some numbers, those are numbers for the whole France, okay? On average, the penetration rate in France is 2% of EVs. And if you make the computation, this boils down to a little bit less 1 million electrical vehicles running in France. Now, if you multiply this quantity by an average capacity, which is 40 kilowatts, you end up thinking or computing that the storage capacity, maximum capacity in the whole park of vehicles, only 2% is equal to 32 gigawatts. So I don't know if you know, but each nuclear central produces 1 gigawatt. Okay, so the full capacity there is about 32 nuclear central power sitting in wheels.
So did France so far subsidize electric vehicles?
A little bit. I think they have like between 5 and 7K euros for each bio vehicle. Yeah. But it's going a bit down according to the policies you could see in Europe, you know, that we should go, we should not go. Now, of course, you are not going to withdraw or you're going to fill fully, okay, this capacity. So what this is the percentage of the battery that you potentially can use for playing this game. Assume that it's just 10%. But even with 10%, means that you have 3 gigawatts capacity to go into this electricity market. Okay, but if you put this number a bit higher, say 30% of penetration rate, you know, I changed my slide because before I have 2030 here, but I don't know what is really happened at that particular time, but it may happen at a certain point. Well, this rise to 50 gigawatts about, okay, if only played with 10%. So it means that it became a serious game if we really go into this high penetration. Okay, so I just put some number. So thinking the vehicles are batteries over wheels. By the way, I generate this picture by ChatGPT, and I explain, give me some cartoons for the idea. This is the evolution of in Europe up to now, up to the last year. So what has been happening is at the beginning, what kind of exponential growth. So everybody gets very excited on that. The policies in Europe are pushing this as much. Then things change a bit because the price of energy, because this and that, but still growing linear. Okay, so where we end up, we don't know, but it will keep growing now. Okay, so there's another picture to show what all the players that enter into the business of electric vehicles. So what I'm talking here is about having a model to describe two things. I call mobility basically is the number of vehicles moving from one point to another. And the state of charge is the average energy carried by this energy flow, by vehicle flow. I'm not doing this at the microscopic level. I'm doing this at the macroscopic level. What I'm interested in at the end of the day is to have regions that capture the concentration of energy in the space and in the time. And I can use this model for predict what is going to be the demand of the vehicles in a given location of the city in terms of concentration of energy and how this concentration is distributed along the time. It's in the morning, in the middle night, and so forth. So for that, we need to have, and this is the first part of my presentation. Now, but this is the weather broadcasting part. So you can compare this with a weather broadcasting system where you have very precise model, you calibrate the model, and then you use it for different things. Now, all the players in the system can be more or less explained here. So these things are connected, vehicles are connected with a grid, and there is business of people that, operate the charge stations called charge station operators. And then there are other players that distribute the energy. There are others that transmit the energy. There are others that produce the energy. The production of intermittent energy, and in the middle of this, there is this energy market. Okay, so when you deal with this type of problem, you have to consider all these different relations. So what I'm now concentrate is how to build the models to predict in time and space the mobility and the state of the mobility here means things in terms of number of vehicles sitting in a particular place at a particular time of the day. Now, all these layers of players and all these difficulties that eventually the arrival vehicle will bring, it can be turned into opportunities, right? So these models, what are used for, it can help in evaluate the impact in the penetration rates of the EVs in the charge station infrastructure. So this is clearly a question that the people that decide, that invest the cities, how many charge stations we are going to allow, where, and which power. So there is not really tools today for doing that. So if we have a mathematical models, we can formulate problems that reply to these questions. We can also refine it, the locations and the power associated to that particular locations. We could combine the models of mobility, state charge with the model of the grid to study the resilience of the network, in particular in terminal points. They're very interesting because if the demand increases, in particular in suburban areas, well, the lines are not dimensioned to eventually cope with this new request, new demand. And there is a solution is to bring a new line there, but that costs a lot more. And then, of course, you can start to play with prices to say, okay, can we move this demand from one area to another to cope with this problem? And the last vision is to see the vehicles as virtual connections that can bring energy from one point to another point because you carry this energy in the battery. Okay, so those are some sort of opportunities that vehicles bring into us. think I move a bit more here. So here it picturizes what I would like to do in the next slides. So the first thing, I would like to write down a model, okay, classical model, dynamical model, with some parameters I will explain. And I would like to connect the model with the market, electricity market. So in the process of who get money from out of this, you have to simplify those that operate the charge station operators. And basically this is the place where the optimization process is going to happen. Okay? Then eventually you could deal with the so-called aggregators. The aggregators are kind of businessmen that buy energy one side and sell the other, so a trade of money. So they will be more or less will be also incorporated there. And then at the end of the day, you have to decide in which market you are going to operate. Though the frequency containment reserve market is the one that we're addressing here, because you need to operate it, react in a very short scale. Remember the first slide I mentioned. So you need also to have some sort of model or to understand how this market operated. So the whole story goes like this. So I have something that allows me to predict what will be the demand or the request. More precise, predict how much flexibility do I have. Then I will offer a couple of information to the market, will be price and power. This information or bits call goes to the market and come back after the market is clear and tell me, okay, then you need to reserve that much power one day after, and that is the price you want to get in case that we use the flexibility you are offering. And then the CSO is going to compute or to optimize what will be the final price you're going to sell electricity to the EVs, okay, to maximize revenues for both, but in particular to the operator here. But of course, it cannot be high price that the one that people pay already. So I have to find some sort of win-to-win policies. Okay, so that's the whole story, and those are the whole change of values that are involved in the EVs. There's another picture I actually do for tomorrow, but I think it's interesting to understand, and I also provide some sort of time frame on the development of the research. So city planners are probably the ones that are close to us in terms of result that we have, because our result allow to reply some of the questions they asked for. The second in the time frame, it will be the charge station operators, because we have some answer for them. And then little by little, these things go into middle long term. So those names that you see here are companies well identified in France, but I think this segmentation is exactly the same basically in any country, okay? So electricity markets, everybody have one. Transmission system operators are those high voltage. Aggregators, the people do business, buy energy in one side and the other. The distribution system operator that distributed lower and middle voltage, and then the charge station operation and city planners. So those are all those. Who do we address? Depends what problem or solution may have. More or less following or tracking this idea of the market segmentation. So we have this, we call it digital twin, and then we imagine some services, right? So there is short-term services that our software could eventually provide. We are not yet. We have these two, more or less, and then these are more long-term objectives. This is a little example of things you can do. This is from Grenoble area. So what you see in this picture is the sum of the average state of charge of the whole park of electrical vehicles, right? So what somehow we look for is to find equilibrium points which are not zero. So the question is, the infrastructure that we have today enough to satisfy the demand of all EVs? Okay? And what you see here is a different plots according to the penetration rates, different scenarios. So when penetration rates are a bit too high with respect to the infrastructure, do you have, the sum of this gone slowly to zero? Means that infrastructure is not enough and you need to add more. And we did some study here that we can show there is some sort of breakpoint after which the equilibrium goes from semi-stable to unstable. So it's like a change of phase. It's interesting to know for a given city, for a given penetration, for a given city, a given infrastructure, what will be this penetration rate. So this is the type of thing we can. The other thing is something which is required in France, I don't know here. It's called strategic planning. So this is the Grenoble area, which is split in little little zones, areas. Each zone is called iris. This is some sort of national division, which is done for all possible cities or metropolis in France. And the public authority need to produce the so-called strategic planning that says for each particular region how much offer of power you need to have in order to provide eventually some incentives to the charge station operators. Okay, and this needs to be done every 2 or 3 years, meaning that you have to produce the same study for many other cities. And then we have compared our optimization with the results that have been produced by some cabinet, probably using some sort of simple rules. And then you can introduce their constraint. For instance, one of the new constraints is that every single public parking need to have a certain percentage of electrical charges. Right? Okay. This is the first version we developed the ERC. I think Omar contributed a bit on that, at least the mobility of people model. Let me just move to this one. This is the second version, which has portability, means that we have been extended the model from Grenoble to any city in France. So here is a record demonstration. Just show a bit what happened with Grenoble, how this system operated. So this is the geographic division. And then you have the number of EVs by region. Those are everything which is sitting here are real numbers. Okay. The model is calibrated using only governmental files. This is a decision we take to avoid to be too much dependent on data. The third generation we want to go through is using data. For the moment, we want to have a proof of concept that the same thing can be portable for any city, and the automatic calibration is done. Okay, now the way we build is we build a graph. So you have origins. So we have information about population, we have information about number of vehicles, and we have information about number of electrical vehicles. In destination, we have 3 categories divided by services, and leisure, workplaces, schools, and hospitals, which are the most predominant ones. Same thing, we have information about number of people working there, and we compute eventually how many people will take the vehicle instead of public transportation and how many of those vehicles will be electric. So those are, again, real data and public data. Then, once we get this information, then we need to connect origin to destination matrices of mobility. We have also information by sectors. We basically summarized all the information. The sector is called EVs. This is the name of things. Number changes, charge station as well. So charge stations are divided into, let me just show first the links. So this is the links from one origin to all possible destinations. Okay. behind this decision, you have to consider the type of destination. If it's a school which is close, the people would basically go to that particular place. If it's a shopping area, there is something called attraction law. So you rather privilege the shops which are close to you than the ones who are far away, and so on. At the end of the day, you get a big graph of that form. So this is really a high-dimensional graph. And to this graph, because we want to also to model the state of charge, then we need to add the charge station, right? So charge station, we have three types. We have home, we have office, and we have publics. For publics, there is, again, real data. So there is a way to recover information. So you know who operated, how many charge stations, and the power associated to each one. From home, we need to have some sort of heuristic model. We have a little bit of information about the average power per house and how many houses eventually have garage, and then from then we end up identifying. And for the office, more or less the same thing. So once we have this, then we go for our choices of parameters. So the main parameter here is the average penetration rate. And then initial state of charge, the power of each home charges, the power of each office charges, the occupancy, because not all, for instance, public charges are occupied 100%. It could be 20%, 30%, and so forth. And once you set these parameters, then you can run the dynamic model, which I will explain if I have time, but I probably will. And then you will see, let the simulation go a bit. Now you can see here the run. There is just 1 week run. The different columns mean different values of stage of charge. This is in percentage. So you go from 0 to 100 according to the time, according to the. And in the right, you have a couple of figures. In particular, this one I mentioned before is the average state charge. You can see how the average state charge goes up and down according to the number of charging stations. So apparently, Grenoble will have enough infrastructure for the moment, given the penetration rate is not too. You can see also this in terms of absolute kilowatts. And this is for the running part. So this is one kind of service you can provide. Say, okay, given the infrastructure, given a city, now, yes, it is enough to satisfy because I know that the state charge average go there. There is another tool here, it's called optimal energy distribution. Is this a strategic planning issue? So in here you have also some few parameters you need to select, and then you get some static map that says, okay, in that particular region, you need to have that much energy per kilometer as a offer for EVs, right? Fine, so I move a bit on. So you give an idea, maybe I used too much time, but I think this is the most important part. I think it's really the message. Now I'm going to zoom into the model itself. Okay. So the model we start with the mobility of people, so whom are participating somehow in this part. So from people to vehicles, which is N, you have to have some sort of pruning. So you have to compute, for instance, the traveling time that you will take between A and B if you use public transportation versus if you use vehicles. If the traveling time difference is large, then we assume people take the vehicles. This is something that also needs to be calibrated, but I think we have a reasonable result from it. So once you have this N, then you have to add to the model the state of the charge. So you have to have computation of losses of energy. So you have to compute between A and B. What is the faster path that potentially the drive will take? Compute the length, compute the average speed, compute the orientation, the inclination. And then from that, you compute losses, delta P. In addition to that, you have to compute how many energy you will inject. And this comes from the charge state, right? So you put this information inside, making a balance of energy and then you end up with the model having these two things. So conservation of mass here, energy balance is there, physical model as a result. I'm going just to flash general idea. So this is the way we compute things. So node has two variables, n and epsilon. Just talk a bit about n. So it's nothing else that the rate of change of the mass here is equal to the difference between inflow and outflow, right? Second thing is what I mentioned before. How do you go from people to vehicles? You have to compute this probability to use the vehicles, which depends on a particular parameter, which is a different traveling time different between if you take buses or if you take your own vehicle, right? So if this probability, if this delta t is small enough, you rather go use public. If not, then you take the car. And that produces probability P that you multiply to the flow of people, and then you multiply by penetration rate. So penetration rate became a parameter, physical parameter within the construction of the model, which I think is nice because then you can make several scenarios with the model. For the introduction of the injection of the power is a little bit more tricky. So again, here for the balancing, you use power balances. So energy in one of the nodes is equal to inflow power minus the inflow power. And you consider also the losses during the path that you went there. Not going to the details of the equation, but basically, then you have this idea of power in and power out and losses. You put these things together, you end up with the original equation. How do you inject the energy is a bit tricky. For the origins and destination, things are not too complicated. Basically, it's a scheduling variable times the number of vehicles sitting there, maximum number of vehicles that you're supposed to be there, having local parkings. The office charge is the same thing. So these two things is the average power, and somehow here the five functions are these scheduling functions that say, okay, people will charge in the night or will charge in the weekends or whatever, right? The more tricky thing is how you introduce a public power injection, because there, you have to start to put into the picture something about how the people behave, right? These things can be pushed a bit to the stream, but in that particular model, we simplify a bit things. So we just considered an injection of energy. We are not yet at that moment, but we do it after. Consider the number of vehicles sitting there. So for the equation of values of energies, I just want to know how much energy do I inject here. So I need to consider if eventually this guy were charging before, because there is another charge station a little bit before. And if charge before, I have to consider this for the charge station, which is in a bit longer, far away from the path. All these considerations can be put in the model. We use some sort of demand and supply formulation for that. Well, the first thing we do is to decide which charge station will be connected with a particular path, right? So if it's too far, probably people will go not there, so will not connect it. If it's connected, then we need to decide how much power do we inject. There are the two phases in the process of construction of the model. Okay, this is what I mentioned before, is the probability to use the cars with respect to probability to use the transportation, public transportation. I'm just moving up, so that's something you already see. So this is for the model, and then what I show you is a bit of open loop evolution of the simulation, right? So I don't know if you have any question at that level before I move to the market electricity formulation.
When you say that you tune the model, can you describe? I mean, it seems like a mess, right? How do you tune the parameter? Can you just give one example or so? How?
Okay, say for the mobility part, This is based on the parameters which are sitting here, and these flow functions basically are, CTS, cell transmission model. But imagine those are the cells. Yeah. So I will use the mean between the supply, the demand and supply. Okay. So parameters are capacity at the level of the supply, capacity of, supply and demand, right? So for instance, physically speaking means number of people that live in that particular area, number of people that potentially would like to go to this place. So capacity here have a real meaning, means for instance, if it's a school, we know there are that much students go there. So we use information about how many students go to that particular place, how many people go to the particular hospital, how many people go to a particular restaurant. How we know that? Because restaurants need to declare their capacity because reason of security in case of fire and so forth. So we know, for instance, this restaurant had that much table. This is in the tables, in the files, public files. So we build some sort of robots that go and pick up the files. There is 20 different sources of files, public files, and go and scan the information we want to get.
Yeah, I have actually two questions. First is maybe a comment, but in modern urban planning, people try to avoid having cars in city environments, and politicians try to get rid of cars. So isn't there a political force to maybe not build charging? Because if you build it's like building roads. The more roads you build, the more cars you get. The more charging points you build, the more cars you get. So do you take that into account, kind of urban political planning, trying to get rid of cars into your model?
No, because these political decisions are changing. For instance, there have been incentive to install chargers, yeah? Because we're talking about 2%, so easy to say, well, in Paris, chargers all around, even if there is no EVs, but we'll put chargers all around, right? And at the same time, we close the roads. And then they open the roads for bikes, electrical bikes, and they close it because their people are unhappy, and then they open for...
No, that's what's happening.
Okay. So I don't take care of that for the moment being, I am just trying to reproduce whatever do I have today. Yeah. Now, if the political change means the mobility may eventually change. That's why we want to go into this third version of the model, which could be calibrated by using data, phone data, mobility phone data, which is more dynamics, right? So now you can see whatever politic the people takes and the mobility. So this is one piece of the cake. The other piece of the cake is, okay, where do we put the charge station? I'm not suggesting to put there. I'm just computing that if you want to satisfy the demand of whatever vehicles, electrical vehicles do we have, we need to have that much surface, right? Where do we put?
I was just wondering if you're considering if you can expand your model to include kind of political dimensions on that. So that was more kind of like.
I have been thinking that, but I don't.
It could be a tool for politicians to also, understand better what happens. What is the.
No, I think that would be reflected in the politics of, for instance, in Grenoble, we have this ecology government, local one.
I have also a second question, if I may. We see a major challenge today in going to green electricity production is that if you install a lot of solar power and a lot of wind energy, then if there is sun and if there is wind, then they produce so much that the prices drop, and so you can't pay back your installment cost. And this is a major challenge for society at the moment. And can your model help somehow to set the pricing in the sense that that you create incentives for anyway going, for circumventing this problem? You see what I mean? You could use your model to extract a pricing model that helps the green transition by making sure that the money is flowing in the right direction at the right time.
Yeah, that is, I think, possible because it's a little bit what I want to talk next. We also look at this curtailment problem. So when you have overproduction and you don't know where to store the energy, then you basically either stop the production of the energy, you kind of short circuit, right? So the only possible way to optimize this thing is to store the solar production somewhere. Yeah. But then again, I think the message is you can formulate different problems. So which problem do you want to formulate it? I think it's possible, but it requires a little bit of work. Knowing what I will show you, we'll see that it's not that straightforward. And the other thing I'm really sensitive is scalability. Okay, I'm a bit tired of doing academic toy examples. You know, put it in a box, you close the box and nobody look at it. I would like to bring this to, so every decision I take need to be thought in a way that can bring it to scalable and is possible realistic. Otherwise, we do not have impact in the society. I mean, we can be convinced ourselves, you know, we are the champions, we do very, very nice math and so forth, but it doesn't leave the room from here, not good for anything. But it's not easy work, because just to know what is a good problem formulation,
it's very difficult.
It's a bit complicated. I will explain my story, why I end up with this. You have another question?
Yeah, another question. Exactly on this page, I think this human mobility from moving from one origin to the destination in a city scale is really the most important thing that's causing the change of EV density and EV SOC density. And I guess my question is, I see a lot of the results are related to how big is a box or of each, like is the granularity of the model. And if you combine two like hexagon or two places together and run the model on higher or like a more sparse granularity, and it should match it should match the model with a finer granularity. And I wonder, like for this formulation and this parameter tuning, if you, for example, in the new model, combine two places into one, does it still have the same result and same distribution, or that will change based on?
So what we did is we first start with the granularity of communes, and we have every single restaurant model. Okay, so then we aggregate the restaurant of one communes, and we realized that this IRIS new geographic distribution was much more smaller, and for some political reason was interesting to match this geographic distribution. So we move into that. We basically bring us to, in some cases, separate out some of the things we have been aggregated, and then even in that case, we can have different leisure places to go, and then we aggregate all at the level of the iris. But it is not really too big, really not big. So when I show these areas with different colors, what we do is we aggregate the value of the state of the charge of each single node which is sitting in this area. So the model is not running to the, say, at the level of areas. They're really running at the level of nodes, and then we use this information to aggregate it and to display the information. But the aggregation things we have been playing with, and we have been moving from one to another, so it's possible to have much more refinate if we wish to have more refinate, or less refinate in some cases because it's just too detailed. So we can change a bit the scale of aggregation. Are we done? Okay. In the remaining time, let me just mention a bit this part of so I come back to this how to optimize renewables information using eventually the storage of vehicles. Let me move on a bit more. So the components of this discussion will be that one. At the very end of my slide, we have a case where we have two stations competing and proposing prices, right, to attract drivers. The other vision here is that you want to connect models from the market of electricity, optimization of prices, and use the model to predict how much energy potentially you can offer. I will explain this more in detail later when I talk to the market, but just to match the interest of this discussion is that we have the model here, chart station operator basically will be the optimizer, and the primary reserve FSC market which we need to have some sort of model to capture the whole picture in one equation, okay? So another thing that changed also a bit here is that since we would like to have a model that use prices, we need to have something we may call here the driver behavior model, okay? So given some price, the intention to go to a particular charge station will be higher because the price is low. And this is type of these curves that you can see here. According to the price, if the price is lower, then beta here is some sort of split ratio between drivers going here and try to charge. So you will be attracted by that station if the prices are low and if your state of charge of the flow is low. Okay, these two conditions. And this is reflected by this type of equation. So this is something we added to the model I just presented. So you package this model. Now I'm not going to give detail, but just general. So you have the full state, which is basically composed by the number of vehicles in each of the nodes and the state of charge associated, right? Then it will depend on many other things. Now it depends on something that will become our control variable, will be the price of charging. And these two variables have to do with the market that I will explain. Now, how the market, I don't know if you are aware of that, operated. There are many markets. This is called one ahead electricity market. So one day ahead, you have to decide how much energy potentially you can offer to go into this market. So you do a bit, a couple of values. So you say, oh, I can offer that much power to play in this flexibility market. And then I offer this power at that much price. So, and then you are not alone. There are many competitors. And then you place the offers in a growing order. Okay, so this is me. There is another provider, and so forth. And then the other hand, you have eventually the demands. And when the demand and supply coincide, then this particular value, which is tau m, that will be the price of market. M stands for market, and B stands for bit. So I bid that amount of power at that price. Since I was proposing this energy, a lower price, probably I will get back my offer. The price in return will be this, much more higher than that, okay? So there is two variables that I propose. There is two variables that I come. In principle, you get the price and the amount of energy that the market requests. In general, if you are in this zone, basically these two things are equal, but if you are in the middle, that could be a slightly different. And this is something you have to do one day before for a slot of for 4 hours during the day, okay? So there is 6 bits you have to create. So what the model is used for is that if you go to propose an amount of energy to the market, you need to predict eventually how many vehicles will be sitting in the charge stations and compute what will be this prediction, right? So the idea is that given some price, we may run this model and compute this amount. This is the total power sitting in the aggregated state station, right? But since I have to sector the market in slices of 4 hours, so I cannot propose that much because at that point, I don't have that much energy, okay? So I have to take the mean of whatever curve do I predicted as being the maximum power that I can put into the market. But since the market is up and down, sometimes they will ask you to reduce the energy, sometimes they will ask you to increase the energy. You have to take the half of that, okay? So this yellow line here is the yellow line that will allow you to construct the model, and this is the amount of energy you can eventually go and propose into the market, okay? 1/2 of the. If you want just to play with the 10%, well, you have to just scale this to 10% of the value. Now, this is the way you put things together, and this is the only slide which is a bit mess, but I just want to show you the complication of that things. So, given that you can predict the amount of energy potential that you will have the next day, and you take the half of that by period of 4 hours, and this is the potential bit that you are going to propose for every slot of hour to the market. Now I put in price 0 because it doesn't cost anything, almost anything, to the charge station to generate this energy if they know they have the vehicle sitting there. Of course, there will be some incentives to the user and blah, blah, but the cost of production is 0. It's not like a generator need to inject gas in order to produce electricity, and that will have some cost, right? So it's very more likely that whatever amount of energy you propose to the market will be taken because your price will be very low. And that's why I'm making this hypothesis. So whatever you propose as a power, this is the one that the market will retain, and the amount of the price that will come back depend on the, I'm not going to tell certain things, right? So it will be some value. The other thing is that how much of this maximum power that have been reserved will be requested. This is something I don't know. Depends on the next day generation of renewable and so forth. So delta P is this amount of the energy that it will be requested to the charge station operated by the transmission system operator. But the only thing I know that it's going to be in a bound, which depends on this P market that I got back here. So this is something, this information I know. So I know the bounds, but I don't know exactly the precise quantity. So I assume that delta P, the amount of energy that I need to extract the amount of energy are going to be used in this market is a random variable bounded by these two values, right? So I need to solve this equation. I'm talking just solving the equation. I'm not optimize anything for non-beam. That depends on the price that will be set next day. Assume you have some information that I want to sell my energy at that one price. The optimizer will do that for you. For the non-beam, this is a fixed amount. The amount of power that you enter into the market, so this is PV here, but depends on X itself. So some sort of non-causal component appear there because it's something you need to know for the next day. And this is something which is a bit uncertainty, but you know the bounds, okay? So at the end of the day, you want to solve this equation to do this prediction, but of course you have some unknowns there. So we formulate this optimization problem that is used only for solving the open loop equation, given some value of price. I need to solve this. What is these things? This is a quantity that is a dummy variable that I added, saying that I don't know how much power I'm going to sell, but I know this power is bounded by the maximum production divided by 2 in the intervals of 4 hours time, okay? So I want to maximize this value, knowing that this is an equation that needs to be satisfied. So this optimization problem, in particular, is for some given delta P, okay? I say that delta P is not known, but I will come back to this again. So the first difficulty is that to be able to solve the equation, and this can be done by an optimization problem. But I still have this difficulty that I don't know delta P. You know it bonds. So again, I add another dummy variable here that I know is bounded by the amount of power eventually that I can propose, okay? And then this is a second problem, optimization problem, that is just used to run the equation, right? So you see here, there is a connection between a dynamic equation of the models and the energy of the electricity, right? Now it comes down, the real optimization problem that I want to solve is also, forget this for the moment being, just concentrating the right answer, is that I would like to optimize this selling price energy to the user by, now I would like to maximize this utility function. What this utility function is the amount of power that you sell efficiently during the day, the cost of the electricity that the user pay for. So this is really the money, the cash money, the flow, plus whatever you get back from the electricity market. Okay? So you have two components here. I don't have any proof of convexity, but it looks a little bit convex, meaning that if the price is very low, you will have a lot of vehicles going into this train station, so the amount of power you can sell is higher. Vice versa, if the price is very high, probably nobody will come, and the power you sell is low. So in both cases, you have some sort of optimal, which is sitting in the middle that probably you don't know. But this is this guy that doing the charge station operation that want to maximize his revenue, right? We will come later to, okay, but what about the drivers? Do they pay more? Do they pay less? So the way you formulate the problem is kind of two optimization problems embedded. So the first one is just to solving the differential equation. It's like I say, I want to find the best optimal price that maximize this utility function under the solution of the dynamic equation. So you see, it became a bit complicated, but this is the way you operate. There is other issues here about knowing some quantities, and you can take some open bounds and solve for the same type of problem for the open bound. But this is just some technicalities, I would say. So this is one of the problems I want to deal with. Then the question, how many vehicles do I serve? Do I serve less vehicles or I serve more vehicles? So here is just a small comparison between the vehicles that you will serve in red, in blue, sorry, if you pay some sort of nominal price. We use some good figures like a 0.3 euros per kilowatt versus whatever it comes from the model and optimization. So independently of the earning, we know that we serve more vehicles by this optimization than if you fix the price. So having variable price is more beneficial for serving more vehicles. Those are the earnings between the whatever you get if you fix the price and whenever you get if you, sorry, this is the fixed nominal one and this is the optimization one. So you could imagine you could potentially lose money, but no, you earn money by doing this optimization. Now, one of the last things is this one, which I find more interesting, is that if you have a competitive companies that want to sell electricity, do they do selfish price setting or they collaborate to set a better price, right? So here you have charge station revenue for each one. Variable here is more or less similar to what I had before, so the total amount of energy sell, but here I'm introducing also the cost of the energy that this guy pay to the spot market, the cost of operation, because it requires some operation, and the revenues, the money you get back from the user. And this is again the market revenues. Okay, so I have two stations competing. You have two prices, one for A and one for B. Now, there are many interesting problem formulations you can set here. This is a selfish, non-collaborative, worst-case strategy. So everyone is optimizing his own strategy, knowing that the competitors may have these different values. The price organized for is higher than 3 and 2 and 1 and so forth. So this strategy means that if I would like to set a value for, this is GA, so this is the station A. I take all possible values that my competitor can take, and I take the worst case, so I take the minimum utility that I may get if, because I don't know who is going to be the value the other guy is going to take, right? So I take this, I do this for all lines, and then I take the max value between the red circles, right? And I do the same for the other. So everyone is trying to optimize his own price based on the worst case design, and not necessarily very good idea doing that way. A more clever optimization will be, okay, let's do some sort of collaborative strategy. And what I have now is I have a utility function, which is the sum of the two utility functions of each charge station, right? So one option will be that I just take the max and I fix the price. But this is, you can see that you are taking the maximum price for each charge station. Probably this is not the best choice. But I can do also equity learning allocations, which means that I take each individual cost that people do by selfish optimization, and I do this type of operation. I take this value of the sum of the two and add it and subtract it in the other way around, that have a name for sharing. and then I'll obtain something which is a bit more equilibrated. So station A will win $16, 14. The problem here is that if I do it in a different way, I end up, this is the nominal one. So what happened is that, okay, I can have a better revenue, but of course the price are much higher. Okay, so I don't want that, because I would like that it's a win-to-win. Otherwise, the people will not accept this compromise. Right? So I can do something else. I can try to do the same sort of optimization, but then I don't want that nobody pays more than they paid by using a selfish optimization. So I restrict this optimization to be any price that is lower than 3 for station A, and any price is lower than 3 at station B. Okay, so I restrain the set value, but still be able to compute revenue, which is much more higher than the one that I had before, okay, by the constraint, but adding the constraint that the new cost will be smaller than the selfish cost. Okay? So it's kind of win-win strategy. And I, of course, can do this using other optimization tools, but it's more or less the same method, so I will not disturb you more with this. I think that to conclude, I think the ground basis of this is to have a reasonable model. Once you have a reasonable model which is credible, then you can start to move to go to different, say, I call it that service. Just to recall, you have 2 platforms which are open. So if you are interested to play with, you can copy these links. This is just for Grenoble, and you have manual calibration. This is for basically all towns in France. You have automatic calibration. And then here we are sitting to look at for how we use the data to, to bring a model. Previous things, we have a model and then we produce data. So it changed a bit the paradigm. And the reason is one of the one mentioned is that mobility is something very dynamic. It changes quite often. So we like to have a system that use this data to, and then we are open to any collaborations. Thank you.
Thank you so much, Carlos. So